Imagine being an EV driver in a world where lithium supplies are dwindling and prices are rising. Did you know that 70% of the world's lithium reserves are not in China, but in South America? What if I told you there is an alternative that is more abundant and cheaper? Welcome to the world of sodium-ion batteries, the potential successor to lithium-ion batteries. Let's dive into how they work and why they are the key to our energy future. Let's start with a quick comparison of sodium and lithium occurrence on Earth. So sodium and lithium are both alkali metals that have become key to battery technology and renewable energy storage. Now, while lithium makes up only 0.0065% of the Earth's crust, sodium is the sixth most abundant element on Earth at 2.7% of the Earth's crust. So that is already encouraging. Now, lithium reserves are concentrated in just a few countries like Chile, Argentina, Bolivia, among a couple others, which can of course cause supply chain issues. In contrast, sodium is widespread around the world, making it way more accessible. What's interesting is that currently lithium prices are at historical lows, which is counterintuitive given its scarcity, but this is due to a rapid expansion of lithium manufacturing capacities. Basically, demand increased, so suppliers dramatically increased production in response, but they managed to do that a bit too well and created an oversupply. Of course, the question here is how this trend will play out in, many years into the future as lithium does become more and more scarce. Now, the abundance and ubiquity of sodium, of course, makes it a promising alternative to lithium for large-scale batteries. Sodium-ion batteries have great potential as a low-cost option for both electric cars and for grid energy storage. Compared to lithium, sodium's low cost and general availability make it an attractive option as these lithium reserves dwindle over the years and prices are sure to skyrocket. Now, the two substances have similar chemical properties, so transforming current lithium production to sodium is not a big issue, which is also a plus. Next, I want to zero in on the usage of sodium-ion batteries, specifically in EVs. So, as already mentioned, sodium batteries can replace lithium and also the use of critical metals like cobalt, manganese, and nickel. So, is anyone taking advantage of this? Yes, they are, as a matter of fact. So the two main companies, CATL and HiNa Battery, are already working on the development of sodium-ion batteries. There might be some smaller ones working on it as well. These are the two major players, so that's who I'll be talking about today. Sodium-ion battery prices should be lower than lithium-ion batteries. A complete battery pack could fit under 1,500 euros. That would, of course, be great news. It would dramatically lower the acquisition costs of electric cars. In February 2023, carmaker JAC Motors announced a test run of the HiNa Seahole E10X vehicle using sodium-ion cells. Now, JAC Motors is part of the JAC Group, which is 50% owned by Volkswagen. So, there is a chance that Volkswagen can also get this sodium battery technology in time, which would of course mean that its promises about low prices for two small upcoming electric cars, the ID.1 and ID.2, could become a reality. That, I think, would be great. Now, HiNa Battery currently mass produces these types of sodium cells with energy densities of 140 to 155 watt-hours per kilogram, which is very interesting. According to current reports, CATL's sodium battery prototype has very good low-temperature performance, maintaining 90% capacity, even at negative 20 degrees Celsius. And it can also accept higher charging currents than lithium-ion cells. So that all looks very positive. Sodium-ion batteries do have the potential to significantly improve EV performance, range, and costs. But of course, it's also necessary to consider the disadvantages compared to current lithium-ion batteries. So we'll take a look at those a little bit later. Like lithium-ion batteries, sodium-ion batteries work on the principle of ion movement between the positive and negative electrode. So the positive electrode or cathode is usually made of a material containing sodium, such as an iron sodium phosphate, for example. The negative electrode or anode is going to be made of a material that can reversibly bind and release sodium ions. This could be a hard carbon or graphite. The liquid electrolyte allows the movement of sodium ions between the cathode and anode. And this is very important for both the overall performance and the safety of the battery. The separator prevents direct contact between the cathode and anode, but it allows the passage of sodium ions and electrons during charging and discharging. During discharging, sodium ions are released from the cathode and they migrate through the electrolyte to the anode. So this creates free electrons at the anode, which then create an electric current that will flow through the connected device back to the cathode. So during charging, sodium ions move in the opposite direction from the anode to the cathode, of course. So that's just a quick overview of the principle of operation in a sodium ion battery. So what are some of the main advantages of using sodium ion as opposed to lithium ion batteries? Number one, which I already mentioned a bit, is of course the abundance of sodium. So sodium is a much more common element than lithium, so it's practically an inexhaustible resource. It is also widespread around the world, so the production is not dependent on just a few countries. It really opens up the market to a much more varied supplier pool, and that's very good. We also have the lower cost, so due to greater availability and easier mining, sodium batteries should be cheaper than lithium ones. That, of course, would allow for more, widespread deployment for energy storage and for EVs. They also have similar chemistry. So sodium is an alkali metal similar to lithium. So the chemical processes in sodium ion batteries are analogous to lithium ones. So this means that production lines that are already in use could theoretically be pretty easily converted from lithium to sodium. We wouldn't have to build new ones. Then we have sustainability. So sodium is both more available and its mining has smaller environmental impacts. In addition, cobalt-free cathodes based on iron, manganese, or vanadium can be used. So there we have, again, fewer precious metals being used. And then the batteries themselves, they withstand higher temperature fluctuations. So CATL's sodium batteries have good low temperature performance and the ability to withstand higher charging currents than lithium ion batteries. Then the HiNa battery, sodium batteries have a safe operating temperature of up to 80 degrees Celsius. So that's pretty good. And from the other end, the operating temperature starts at negative 40 degrees Celsius. So you see there's just like a bigger window there. The stated lifetime is 4,500 cycles before the capacity is reduced to 83% when discharging or charging at a current of 2C. So that's impressive. Of course, we also have to look at the disadvantages. So, for example, the lower energy density. Sodium has a higher atomic mass than lithium, so sodium batteries do not yet achieve such high energy per cell weight. Although sodium batteries are theoretically capable of storing relatively large amounts of energy, up to 792 watt-hours per kilogram, which is almost twice the maximum of lithium-ion batteries, these values are only theoretical. So in practice, today's lithium batteries are significantly better in this respect than sodium ones. Just to give you an idea, a sodium battery from CATL has an energy density of 160 watt-hours per kilogram. This was presented in 2021, while lithium-ion batteries today have above 300 watt-hours per kilogram. That is a significant difference. It is also a less mature technology. Sodium battery research is still in its infancy, while, lithium-ion battery cells have, of course, been mass-produced for decades now. So there's a lot more experience behind it. They also have a shorter lifespan. So some sodium batteries exhibit lower stability and shorter lifespan than lithium-ion batteries. However, the manufacturer HiNa Battery does claim its sodium battery has a lifespan of over 4,500 charge cycles. So, it's a question maybe of just further development there. There's also the disadvantage of inconsistent performance. So the performance of sodium battery does depend on the exact combination of materials. And since only a couple companies have started making sodium ion batteries at this point, we don't have much data here or access to any tests that have been done regarding performance. Of course, as sodium battery EVs start hitting the market, we can look forward to that information starting to come out more and more, hopefully within just a matter of months. I also want to look briefly at recycling and referring to lithium-ion batteries as LIBs and sodium-ion batteries as SIBs, just to save some time and some words. So LIBs are more difficult and costly to recycle when compared to SIBs due to the wide variety of LIB chemistries, package styles, and materials. LIBs contain higher value materials like lithium and cobalt, but the cost to separate and recover these materials through recycling is currently higher than sourcing new ones. So that's not good for recycling. Now, SIBs have fewer package styles and chemistries, which makes recycling simpler. But here the materials have, of course, a lower economic value, and that limits commercial recycling because it's just not as interesting. Still, SIBs may offer better sustainability when considering environmental impacts and also social factors like the alleged human rights abuses that are associated with lithium and cobalt mining. At this point, effective recycling processes for both LIBs and SIBs are still being developed. Achieving real sustainability will require optimizing the batteries and recycling processes together through this design for recycling approach. Now, this is something we're seeing with all kinds of products today. It's a concept within the larger framework of establishing a circular economy approach, where products are created to be easily repaired and easily and effectively recycled, as opposed to this take, make, and waste model that most of our economies have operated under for the past several decades. Personally, I think a circular economy model is a great goal to work towards, EVs included. So, this design for recycling approach, I think I give that a thumbs up. I hope it becomes more and more important. Of course, we also want to compare them in terms of some other parameters. So in terms of performance, sodium-ion batteries do not yet reach the parameters of lithium, but they are suitable at this point for less demanding applications such as static energy storage, freight electric vehicles, shipping, or backup power sources. And hopefully, as the technology matures, they will also become an increasingly attractive option for use in personal EVs. Regarding lifespan, the stability of sodium cells is constantly improving and approaching lithium. For some chemical compositions, a comparable lifespan in the order of thousands of cycles is expected. Then in terms of safety, sodium batteries will still have to undergo testing, but certain chemistries could actually be safer due to the higher stability of sodium. So it all looks pretty promising. So as you can see, despite a few disadvantages, sodium batteries today have considerable potential to become a cheaper and more environmentally friendly alternative to lithium soon. The main advantages, of course, are the availability of sodium, the lower costs, the similar chemistry to lithium, and the lower environmental impact. So sodium cells do not yet achieve the high energy densities of lithium-ion batteries. They are at this point still very suitable for less demanding applications. But keep in mind, this is a very new technology, so continuing research is bringing constant improvements to sodium batteries, improving the lifespan, the performance, and the safety. There is a real chance that they will replace lithium-ion batteries in many areas, including in EVs. And I personally look forward to that very much. I think there's great potential there. They really represent a promising lithium alternative for the future. And by that, I basically mean, the year 2024 and onward. I think we're already seeing those changes, and I think we can see, huge changes coming in the future, which will be great for the industry. It's really going to it's really going to take care of a lot of those concerns, the higher costs, the environmental impact, all of that. Sodium-ion batteries really help take care of that. So that's good stuff. So that's all I have for today regarding sodium-ion batteries. Let me know your thoughts about this technology in the comments. I'm curious to know if you're like me, looking forward to seeing more sodium-ion battery-powered EVs on the road. Also, what do you think about this design for recycling approach? Will it become a focal point for manufacturers? Or will they, remain happy with the way things are now? I definitely look forward to seeing all of you guys in the comments section. As always, thank you all for watching, and I'll catch you next time.